Classifying sets and subsets of real numbers. Real numbers are the set of all numbers that can be represented on a number line. And within real numbers, we have different subsets. Natural numbers are the set of counting numbers. Whole numbers are the set of natural numbers and 0. So you can see over here with our natural numbers, we had 1, 2, 3, 4, 5, and so on, just like you learned how to count. And then for our whole numbers, we have all of the natural numbers and 0. Integers are the set of whole numbers and their opposites, including 0. So here we're going to have all of the whole numbers. And remember, whole numbers include 0, so natural numbers in blue, 0 in yellow, and then their opposites also, right? And those are the integers. And rational numbers is a much broader set. It's the set of all numbers that can be written as a ratio of two integers, where the denominator is not 0. So natural numbers, whole numbers, and integers, these are all rational. And we have a lot of other things that are rational as well. We have positive and negative values, and we have values that are fractional. We have values that are decimals. The key thing here is that these are all values that can be written as a ratio of two integers. So for example, this 3 1/3 here, you might be thinking, hey now, that's not written. I wouldn't know how to write that as a ratio of two integers. Here's how you would do it. 3 1/3 as a mixed number is 10/3. I mean, as an improper fraction is 10/3. And 10/3 is the ratio of 10 and 3. 10 and 3 are both integers, so 3 1/3 is equivalent to 10/3, and that is a rational number since it's a ratio of two integers. Also, check out this one over here, the square root of 9. You might be thinking, well, square roots, I don't know if those are rational. This one is because this is actually just 3. Right? In fact, 3 is a natural number. So that's something you need to consider is what other sets could this number belong to? Because the square root of 9 is rational, but it's also an integer, it's also a whole number, and it's also natural. Numbers can belong to more than one set. Irrational numbers are the set of numbers that cannot be written as a ratio of two integers. Pi is an example. Remember, it goes on forever. 3.1415926535892. It goes on forever, right? The square root of 2 is not like the square root of 9. 2 does not have a perfect square. There's not a number that is an integer that I can multiply by itself to give me 2. This would result in a decimal that would go on forever. This number down here too, this 1.2434871. Do you notice that none of those numbers seem to be forming a pattern? This is also an example of an irrational number. The digits are going to go on forever and they're never going to form a pattern. So I can't write that as a ratio of two integers either. All right, those are our definitions. Those are the sets of real numbers that we need to be able to consider. Next, we're going to talk about how to organize these values. But before we start organizing them, I want to talk a little bit about how a map is related to these two different types of diagrams that we're going to use today. This little square right here represents Dallas County. Dallas County is inside Texas, and Texas is inside the United States. If you're watching this video from a Garland ISD school, you are inside Dallas County right now. So I'm going to start creating a diagram, and right now I'm just going to create one region. It's going to be my Dallas County region. Should I put our Garland schools inside of Dallas County or outside of Dallas County? Inside, right? All of our Garland ISD schools are located inside Dallas County, so it's going to go inside the bubble. If I were to put it outside of that region, I would be saying that the schools are outside of Dallas County. But all of our schools are inside that little square rectangular area right down there, right? Now, another question for you. Are you in Texas right now? Yes, you are, right? So we could add another region here, and we could say that you are in Texas. So this blue word, Garland, it's currently inside the Dallas County bubble, and it's also inside the Texas bubble, right? Now, I have a question for you. Could I write Garland out here? Would that be okay? No, it would not be okay, because if I write it in this region, I'm saying it's outside of Dallas County. This word is written outside of the Dallas County circle, outside of the Dallas County region, so that would be an incorrect place to locate that. I would be saying something that's not true. You can't go there. Let's draw another region. Here we go. This is going to be for the United States of America. I'm going to write United States. And we're inside the United States, aren't we? Because Texas is inside the United States, Dallas County is inside Texas, and Garland is inside the United States. Could I write Garland here? We're in the United States, right? No, I cannot. Because if I wrote it in this section, I would be saying that Garland is outside of Texas and that Garland is outside of Dallas County. If I want to indicate that Garland is inside Dallas County, I need to put it inside the Dallas County circle, which is already inside the Texas circle and inside the United States circle. So this is the only location where it is okay to put Garland, because Garland is inside Dallas County. And that's what you see on the map right there too, right? If we zoom in, this is where we are right now. We're also inside our Texas boundaries, which are actually pretty hard to draw. And we are inside our United States boundaries. This looks a little bit more complicated than our diagram, doesn't it? The diagram is an easier way to show these relationships. Now let's try it with some numbers. I'm going to use this to represent whole numbers, and this side is going to represent integers. And then we'll do the same thing with our Euler diagram. The inside is going to be the whole numbers, and the larger region is going to be the integers. Let me change color of pens. Let's classify these four numbers up here. We want to locate these in these diagrams. So I'm going to start with -1. And let's just think about what sets this belongs to. Is -1 a whole number? No, my whole numbers are 0, 1, 2, 3, 4, 5, and so on, right? I don't have any negative whole numbers, so it doesn't belong there. Is -1 an integer? Yes, it is, because the integers includes the whole numbers, their opposites, and 0, because 0 is a whole number. How about 0? Is 0 a whole number? Yes, it is, and it's also an integer. The square root of 4, let's talk about what number this really is. The square root of 4 is 2, so this is just a fancy 2. It's a 2 in disguise. 2 is a whole number, and 2 is an integer. -5 is not a whole number because it's negative, but it is an integer. All right, so now we're ready to place these on our diagrams. We know which sets they belong to. So we said that -1 is not a whole number, but it is an integer. So -1 is going to go over here. We said that 0 is both. We said that 4, the square root of 4 is both. So it's going to go in here. And we said that -5 is an integer, but not a whole number. Did y'all notice we didn't put anything over in this region over here, right? That's because it's not possible for a number to be a whole number and not an integer. All whole numbers are integers, so there won't be anything in this space. Though we don't really need that space, do we? That's where Euler diagrams become really handy. So we would put 0 and the square root of 4 here because they are whole numbers, and they're also integers, right? They also are inside the integer circle at the same time. We would put -5 and -1 over here because they are integers, but they are not whole numbers. Let me ask a question. Would it be okay to put 0 out here? No, it would not be okay to put 0 out here. That would be the same thing as putting 0 in this area. So the reason that's wrong is because when you place it there, you're saying 0 is not a whole number. But 0 is a whole number. So there's only one space where 0 can go. And the same for the square root of 4. Each number has one location where it belongs, whether you're using a Venn diagram or an Euler diagram. A number can belong to multiple sets, but there's only one location where it goes on your diagram. All right, let's practice. The diagram shows the relationship among different sets of numbers. Place the numbers in the correct group. The first thing that I want to do is analyze these numbers and see, are any of them maybe integers in disguise? Let me think. Could there be the square root of 23? Is there a number that I could multiply by itself to get 23? not an integer, right? In fact, let's go ahead and just figure out what this is. I would feel better if I knew what that value is in decimal form. I'm going to type it in my calculator. So my calculator is telling me that the square root of 23 is 4.79583 something, something, something. It goes on forever. So that is not going to be rational. Good to know. All right, I think the rest of these look good. Let's get started. So I'm going to make some space down here underneath my diagram. The three sets that I'm thinking about are real numbers, rational numbers, and irrational numbers. And let's do negative 4.5 first. So is this a real number? Yes, it's a real number, right? If you can put it on a number line, then it's a real number. Is it a rational number? Is it a ratio of two integers? Yes, it is. It's actually the ratio of negative 9 and 2, right? Negative 9 over 2 would be negative 4.5. Is it irrational? No, it's not. It's not possible for a number to be both rational and irrational. It's going to be one or the other of those two. All right, square root of 23. It's a real number. We could put it on the number line. It would almost be 5. It is not rational because that decimal is going to go on forever without making any pattern. So it's irrational. Let's look at negative 12. It's a real number. It's a rational number, which means it is not an irrational number. 7/8 is real and rational. 1.75 is real and rational. Pi is real and irrational. It goes on forever, and it doesn't repeat or make a pattern. And then 0.6 repeating, this is really 0.666666666 forever, right? So that's real, and it is rational because it does make a pattern. And we'll talk about what sort of integers we could use to make that ratio in a second. It's not irrational. We know that this number is actually just 2/3, right? It's the ratio of 2 and 3. So since it's the ratio of two integers, then it is a rational number. All right, now we should know where each of these belongs. Let's go ahead and place them. All right, negative 4.5 is going to go in here. The square root of 23 is going to go over here. Negative 12 will be over there. 7/8 will be here. 1.75 will be here. Pi is going to be in the irrational side. And 0.6 repeating will be on the rational side. So there's nothing outside of the rational and irrational circles, right? They want all of these numbers go in one of those two, but none of them go in both. So whenever you're classifying numbers, making a table like this is a great strategy to help you be sure that it gets in the right place. And color coding is a tool that can make it even easier. Check that out. All right, let's try this diagram. This one has a lot of regions to think about, but that doesn't mean it's hard. The first thing we need to do is see if any of these numbers are in disguise. I see one right here. The square root of 144 is 12. The square root of 55, that's not a perfect square number. There's not an integer that I can multiply by itself to give me 55. So that one is going to probably be irrational. Let me just type it in my calculator and see what it is. Sure enough, it gives me a long decimal that goes on forever and ever and ever and does not repeat in a meaningful way. That is an irrational number right there. I don't actually see the word irrational on here though. So where should I put my irrational numbers? I don't see the word irrational. Well, irrational numbers are going to be outside of the rational number circle, but they are going to be inside the real number circle, or in this case, the real number rectangle. So irrational numbers are going to go in this region here that's outside of the circular area, but inside of the rectangular area because these values are real, but they are not rational. All right, I'm going to make my little table because that's a helpful strategy. Let's do this. So 3/4 is real, 3/4 is rational. It's the ratio of 3 and 4. It's not an integer, it's a fractional value. So that's where I'll stop. Let's see, negative 92 is real, it's rational. You could actually say it's the ratio of negative 92 and 1, right? It's an integer, it's not a whole number. We don't have any negative whole numbers. 5.2 is real. 5.2 is rational. 5.2 is not an integer. The square root of 144, remember that's actually 12. That's real, that's rational, that's an integer, that's a whole number, and that's natural. So that belongs to all of these. The square root of 55 is real, but it's not rational. It's also not an integer, a whole number, or a natural number. 19 is real, rational, it's an integer, a whole number, and a natural number. 0 is real. It's rational, it's an integer, and it's a whole number, but it is not a natural number because the natural numbers are our counting numbers. So I'm going to start with my two natural numbers. I have 12. Oops, you know what? I should really write that as the square root of 144 because that's what I was asked to do. Square root of 144 goes there and 19 goes there. 0, 19, and the square root of 144 are all whole numbers, but the only one that's going to go in this region is 0 because what would I be saying if I put 19 out here? I would be saying that 19 is not natural if I put it outside of the natural number region. So this is wrong. 19 can't go there. Neither can the square root of 144. They are whole numbers, but since they're natural numbers, they have to go in the natural number circle. Otherwise, I'm saying if I put them outside of there, I'm saying they're not natural. Okay, let's see what's next. We've got our integers, and so that's going to be negative 92. 0, 19, and the square root of 144 are also integers, but I can't put them in this same region that negative 92 is. Like if I put the square root of 144 out here, I'd be saying it's not a natural number and not a whole number. So that can't go there. It's already placed correctly as a natural number. Okay. And then we've got our rational numbers, and here they are, and there's two that I need to add to my diagram. Negative 92, the square root of 144, 19, and 0 are already on my diagram in their correct locations. So now I need to do 3/4 and 5.2. So 3/4 and 5.2. There they go. They are rational numbers that are not integers. Whole numbers are natural. And then I have one more value that I need to consider, right? So all of these numbers are real. All of them can be placed on a number line, but only one of them is going to go in this area out here, and that's the square root of 55. So all of these numbers are real, but all the other ones are already correctly placed in their correct locations. If I were to put 19 out here, I would be saying that 19 is not rational, it's not an integer, it's not a whole number, and it's not natural. That's not true. So 19 doesn't go out here. None of these other ones do. Just the square root of 55, because the square root of 55 is the only real number on my list that is not rational, integer, whole, or natural. So we have classified these correctly, and it wasn't that much work. It definitely helped to use a table. Why don't you pause the video and try this one, and then hit play when you're ready to talk about it. All right, you hit play, so you must be ready to talk about it. First of all, let's reveal our numbers that were in disguise. This is a 6. This is a negative 14. All right, and then the square root of 90 is not a perfect square. The square root of 90 is, in fact, irrational. All right, so let's start looking at these. We know that 18/3 is really a 6. That would be real, it would be rational, it would be an integer, a whole number, and a natural number. Now let's look at the negative square root of 196. So that's really negative 14. That's real, it's rational, it's an integer, but it's not a whole number because you can't have negative whole numbers. 37.4 is real and rational, but it's not an integer. The square root of 90 is real, but it is not rational. In fact, it is irrational. 39 is real, rational, integer, whole, and natural. 0.22222222222 is real and rational. And negative 25 is real, rational, and integer. So first I'm going to do my irrational number, and I only have one of them. It's just the square root of 90. That's the only irrational number here. Next, let's take a look at our natural numbers. Our natural numbers are 18/3, which is really a 6, and 39. Next up is our whole numbers. And 18 over 3 and 39 are both whole numbers, but we're going to leave them where they are. If we were to move them outside of the natural numbers rectangle, we would be saying they are not natural. They are natural, so we're not going to move them. We're just going to understand that they are currently both inside the whole number rectangle and the natural number rectangle. All right, next up is our integers. Okay, so 39 and 18 over 3 are both integers. And we're going to add 2 more integers here too. We're going to have negative square root of 196 and negative 25. Okay. All right. Next up is our rational numbers. 18 over 3 is rational. Negative square root of 196 is rational. 37.4 is rational. 39 is rational. 0.2 repeating is rational, and negative 25 is rational. Now, there are only a couple here, though, that we have not already placed, and that would be 37.4 and 0.222222222, right? There we go. So they are now in the correct area. The negative square root of 196 is rational, but we're not going to move it out of the integer rectangle. If we moved it outside of the integer rectangle, we would be saying it's not an integer, and it is an integer. So we're not going to move anything that we have already placed. All right, good job. Now we're going to look at our real numbers. All of these numbers are real. They can all be placed on the number line. And you know what, though? They are already in our diagram, and they are currently in the correct locations. So they're all real because everything is currently inside the large real number rectangle, right? So would it be okay for me to move the square root of 90 out here? No, because then I would be saying it is not irrational. I cannot do that. It needs to stay where it is. Would it be okay for me to move negative 25 out here? No, I can't do that. I would be saying it's not an integer. It's not a rational number. And it's both of those things, right? So it needs to stay where it is inside the integer region. There's nothing right now that I need to place out here. In fact, in this particular diagram, everything is either a rational number or an irrational number, and we are classifying them in their most specific set.